Hi everyone, welcome to today's session on analyzing models with Wolfram language. In yesterday's session, we discussed systems and learned to use System Modeler. In today's session, we will learn to analyze models using the Wolfram language. For the integration of Wolfram language and System Modeler to work seamlessly, you should have the same version of System Modeler and Mathematica. For example, if you are using version 14 of System Modeler, then you should also use version 14 of the Wolfram language. Before we start, let's take a poll and see how familiar you are with the Wolfram language and System Modeler. This will enable us to understand what we should cover and what we should skip.
Thank you, Cassidy, for starting the poll. I just want, through this poll, we just wanted to know if how many people are familiar with Wolfram language, and if anyone has tried the integration between Wolfram language and System Modeler in the past, so that we know what basics we have to cover in this session. Right. So, Vedant, I see that there are some participants who are new to both System Modeler and Wolfram language. And I guess there are a lot of people who uh, are familiar with Wolfram language, uh, right?
Yes. For the beginners, we strongly recommend to watch the yesterday study group video.
Right, and we will cover some of those basics today. Right. Okay, Cassidy, we can proceed. I think we can close the poll for now.
In yesterday's session, we modeled the coffee cooling process where we used the sliders to observe the impact of the initial temperature of coffee and the impact of ambient temperature. However, as you start creating more models, you will realize that you would want to expand your analysis capabilities. For instance, when you create a model, in most cases, you do not know the exact values of the parameters. You would need to do some experiments and then calibrate your model parameters using the experimental data. It will be time consuming to tune the parameters manually, and you'd want to automate the calibration process. But what about the cases where doing an experiment is tough, or you are more interested in the variation of the output for a range or probability distribution of a model parameter? You would need to carry out hundreds of simulations and manually stitch the results together. For such scenarios, you should want to automate the process of determining uncertainties in model outputs. I just listed two scenarios, but there might be hundreds of other scenarios relevant to your field of study that you want to do, like designing of controllers, doing frequency analysis, or carrying out sensitivity analysis. Integration with the Wolfram language facilitates carrying out such analysis. In today's session, we will use our coffee cooling example and explore a few of such analysis. But before we dive into the hands-on exercise, here are some real-world examples where the integration of Wolfram language and System Modeler was really useful. In the satellite path example, the motion of the satellite was modeled in System Modeler, and the x, y, and z coordinates of the satellite were imported to Wolfram language. Using the geographic and graphic functionalities of Wolfram language, the nearest cities to the satellite and the path of the satellite were plotted. This enabled the modeler to draw further insights from the model. For example, this information can be used to plan for ground stations where the satellite can send its stored data. In this new drug discovery example, the impact of a new drug on a biochemical pathway was analyzed. Sensitivity analysis was used to specify the variation in a parameter value, and its impact on different processes was plotted. This kind of analysis helped in determining the effectiveness of the drug and simultaneously checking if it leads to any unwanted side effects. In this example of an analog synthesizer, a digital model of a filter was created and validated in System Modeler. In order to deploy the filter in a hardware, the equations from the model were extracted and simplified using the Wolfram language. The resulting equation was then deployed into hardware. This type of workflow helped the modeler to quickly iterate through various designs, followed by simplification of the equations to make it deployable to a hardware that operates at a very high speed. We will look into this example when we use models to create music in one of the upcoming sessions. All these examples are taken from our blogs. You can refer to them after today's session if you want to learn more. In our last session, we modeled the coffee cooling process. This example is simple, yet it contains essential dynamics that will help us explore the different analysis functions. For example, we can use it to test uncertainties and calibrate the model parameters using real-world data. Let's use this example for today's hands-on session and do some analysis.
Okay, so before we start today's session, I just wanted to let people know that to carry out all this examples that we will be showing today, you will need version 14 of Wolfram language and System Modeler. I think most of you already have version 14, but if you have version 13 of Mathematica and System Modeler version 14, then there might be some conflicts, and uh, it's we need to have some separate code to connect it. So to have a seamless experience, you should have both the versions. And if you don't have like version 14 of System Modeler Mathematica, you can download a trial, and then you will be able to carry out this this exercise that we will cover today. Okay, fine. Uh, just to just to get started, like yesterday, we created this model of the coffee cooling process. I think most of you would have tried it out, and you would be able to simulate it. If for some reason you feel that you were not able to complete the model, or you feel that uh, your model is not behaving as you expect, you can compare it with the example that is provided inside the solution folder, so you can use that as a reference, right? uh, and so today, if for example you have not completed the exercise that we covered yesterday, instead of the exercises package here, you can use the solutions, the example provided in the solutions folder, but we will be covering it very soon, right? Okay, so to get started, one thing we usually, or I usually do, is I call the system model function. And for people who are new to Wolfram language, to evaluate a function, you go on the line uh, of the function and you press Shift plus Enter, right? And what happens when we run the system model function? It loads all the packlets, or all the libraries that have the functions that link both system modeler and Wolfram language. So this step loads all those functions. uh, to be clear, you don't need to run this function. Whenever you load any function that relates to the connection between mathematic and system modeler, this function is automatically run. But I typically do it to keep all the process to start with a fresh to start sequentially. So first I evaluate this, right? Sergio is the expert and who has been involved in the integration of Wolfram language and system modeler. Perhaps Sergio, you can say something about the system model function call that I'm doing at the start.
Right, as you indicated, this is basically loading the packlets related to the system modeling functionality and making the connection, the link between your Mathematica and your system modeler. It's also a live connection, so you're going to be able to, well, as we're going to see, the things that you do in Mathematica are going to be able to affect the state of system modeler and vice versa. So yeah.
Right. Okay. So before we do any analysis, the first thing that we need to know is the name of the model that we are trying to call. So for people who are new to System Modeler, this name might look very long and might be confusing. But if you read this properly, this is basically this comes from the object-oriented way of defining a model. So here we have our step one exercise our step one model under the exercise folder, which is present under the coffee sub package, which comes under the modeling principles library. So that's how the model is named. Since I didn't do the exercises, I didn't complete the exercise that we did yesterday. I will use the example present in the solutions package. So I will just write solution here, right? And also if I open System Modeler, you can find the name of your model on the top left here on the top left, and then here you can see it's called model principles dot coffee dot solution dot step one. So you can just copy it and then use it as your model name, right? So as you can see, when you are using Wolfram language and system modeler, there is a lot of back and forth. Like I have to minimize my window in Wolfram language, go to system modeler, and then come back from system modeler to the Wolfram language. So there is a way that I can go directly from from the Wolfram language and open the model that I want to view using a command. And that command is system modeler. So people, if you have seen yesterday's notebook, you would have found this function used in yesterday's session. So it's basically when you use system modeler, you give the model that you want to open. So here I will pass on the model name variable, and then I can open different views uh, in system modeler. Let's start with the modeling view. So as you saw yesterday, we have the modeling view, we have the simulation view, and in some cases we have the animation view as well, and also a documentation of a model. And you can open any of those views from the Wolfram language. For now, I'm interested in the modeling view of the model. So I will say system modeler, model name, and then I will pass on the property, and I would click shift enter. And when I do this, you would see that the system modeler screen comes up. Uh, this is helpful when you have a lot of libraries and then you have to open a specific model. You have to drill down on this library, sub-libraries, and open it. So rather than doing that, I can just specify the model name and then use the property of modeling and then open it directly. Right. I would want you guys to just start. Like I will give, like, let's take 1 minute so that you guys can execute these functions and try to open your model using the system modeler function. And if you face any difficulties, please free to post your questions in the Q&A. Sergio, meanwhile, we wait for people to just try out the function that we just showed. Is there anything that you would want to add at this stage?
No, everything is okay. All is good.
Right.
Ankit, maybe I can ask a question.
Sure.
Can we briefly explain why we are using System Modeler and the Mathematica together? So what do we leverage here? Couldn't we do all this either using Mathematica or System Modeler?
Right. As I showed in the initial analysis section, the thing is we use Wolfram language as a scripting thing. So once we create a model, right, we have a specific instance of our model with the specific parameter values, initial values. And once you have that specific instance, you would like to get more insights. And to get more insights, you would want to do a large number of simulations, and you want to do it programmatically, right? You don't want to manually do everything and then get the data from each simulation results and stitch them together. So rather than doing all those things, we use the Wolfram language to do the automated work for us and provide us with a compiled result. And during today's session, we will look at some examples as well. Right. I hope people would have done or would have tried the system modeler function for now. And right. So um, the next function that I typically use is the system model function that we have already used here. And so rather than opening system modeler again to view the diagram, it would be nice that you can open the diagram in the Wolfram language itself. So you can refer to it and don't have to go back and forth. To do this, you call the system model function, pass on the model name, of course, and then you can use the diagram property. And when I do this, it creates a vector image of my model um, of my model. Also, if I want to know more about the system model function, like apart from the diagram property, what other properties are there, I can right click perhaps, and there is no. So I select my function and click F1, and then I can view the different properties that are available, right? So in this case, we saw the diagram, but if you want to read the documentation of something, or if you want to understand what are the simulation settings or the description of a model, you can use all these properties to query uh, different uh, uh, different things. But the most common that I typically end up using is diagram. And just to show you a trick that I also typically do is sometimes I don't like to have the grid outside my diagram. uh, it's just a matter of preference. So I can also remove that frame, and you do that by putting curly parenthesis around diagram and then passing the option frame goes to false. Right. And then you see now there is no frame around it. And it's a personal taste. I kind of uh, uh, prefer this view. And also you can use, let's say you want a different image size. So you can pass in a property called image size and goes to 500, for example. So you can switch, or you can control all these options once you have the diagram, right? But yeah, this is not the interesting part. uh, let's let's get to the meat of it. Okay, so once we have defined the model, we saw how we can switch between system modeler and Wolfram language using the system modeler function. Just to verify that we have the correct model in place and our model works as expected, we can plot the behavior of our model, right? So we can use the function system model plot and pass in the name of our model. And then if I press shift enter, let's see what output I get. So what this function does is it takes the model name, it simulates the model in the background, and it plots the stored plot in your model. Like yesterday we saw how you can plot something, and once you plot something, you can save your result or save the plot in the model as a model plot, right? So when you use system model plot with a given model name, it plots the default plot, right? Vedat, you were asking yesterday what is a default plot and what are the other types of plot.
Right.
So when you set a default plot, that is the plot that is plotted.
So what you are saying that if we don't have any default plot, then we would expect there won't be any plot?
Yes, there won't be any plot. And in that case, you have to define which variable you want to plot, right? So let me open this documentation of system model plot, and then let me go to options, no, scope, and then variable specification. So let's say in this example, uh, in this example, we have system model plot. I pass in the model name, in this case sim, and then I can pass in the variables that I want to plot, and then I can plot it, right? And also, you saw that we had defined various model plots. I can also specify a particular model plot by giving its name. So the name that we use to store it in Simulation Center, we can pass it on and then get the plot as well. Right. Uh, right. Sergio, do you want to add anything up to this point?
Maybe a question from one of the students. So they wonder if it is possible to keep to auto load the library every time you open System Modeler.
Mhm. Um, yes, that is possible. Uh, and perhaps I will take a note of it, and perhaps we can cover it tomorrow, because we can actually create a, a package with an extension called .sma, and then we can set those properties. But I think it's more on system model side, so perhaps we can take it tomorrow. Is that all right? I think, yeah. So I can take it
That
tomorrow,
sounds
or
like a plan.
yeah, okay. Because then I don't want to switch to system modeler now, but yeah, that can be done. Okay, so I would give a minute for people to try out the system model plot function. So just use system model plot and pass in the model name and try to see if you are getting the plot. And if you have any issues, please please drop your questions in the chat. Right. But
So
without, in the
Ankit,
meantime, yes.
yeah, I was gonna ask. So now we talk about system modeler and
Hmm.
Mathematica. Now we are running we are doing an analysis of a model which we had on system modeler,
Hmm.
which is the coffee mug example.
Hmm.
So we are talking at least two models, right? Two files. So where should we store them?
Hmm. Right. So we have a Wolfram language notebook and the math and the model file. Is that what you mean?
Right. Yeah. We have the Mathematica file notebook
Hmm.
and also a system modeler file
Hmm.
model. So where should we store them? So is it okay if I just start a new notebook and without saving it and write and get some results?
Right. Okay. Okay. I can understand. I understand what you mean. So we don't need to put the notebook and the model side by side. The thing is, you need to load the model in System Modeler, and if you have the model loaded in System Modeler, no matter where you have saved it in your disk, Wolfram language and the Wolfram language notebook automatically detects the model that is loaded in System Modeler, and you can run it. So there is no restriction, or uh, there is no such uh,
Mhm.
dependencies there.
Now, because now we download it, everything was in single folder,
Hmm.
and we could easily run that because you
Yes,
prepare everything accordingly.
yes, yes. Right. Okay. So with system model plot, Vedat, I also wanted to give an example. Uh, Let me just simulate my model first. So let's say we have a different variable that we want to plot. So let's simulate our model and find a variable that would be interesting. So now once I have simulated a model, we already have a plot of this, so that's not interesting. Let's create a new plot, and then maybe in the coffee mug, in the port, right, we have the Q flow. This is 0, not interesting. Right. So we have a heat flow uh, to the ambient. The heat is going out to the ambient, right? So let's say we have, for example, let's consider we want to plot this particular variable in Wolfram language. How would I do that? So once I have plotted my variable in Simulation Center, I can just copy the name of this. So I usually double click here, and then yeah, I would just copy the model plot name. Okay, so the way I did it was I double clicked um, on the plot legend, and then in the y data here I just double clicked here, and it gives me the name of the variable that I want to plot. So once I have that variable, I copy it, and then I will go back to Wolfram language and put the variable name here, right? So so I use a curly parenthesis, and inside that I define which variable I want to plot, and then I do shift enter, right? And then you could see that I can now plot a variable that I want, right? I don't need to rely on the saved model plot. So I use a curly parenthesis, and inside that I can list the variable that I want to plot, and I can also plot multiple different variables together, right? So inside this curly parenthesis, I can also list the other variables that I want to plot. So you can plot multiple of them, right? Okay, um, right. So let's move ahead. Um, right. Sergio, do you want to add anything up to this point?
Maybe you want to say something about the units that they are seeing in the plot, but
Yes, yes. So the thing is, when you do system model plot of a variable, the units that you have defined in Simulation Center is automatically inferred, or we try to match the units in System Modeler with the units available in Wolfram language and present the results in the unit of your model, right? Um, uh, Right. And then there are some scenarios where you want to not use, or you want to use the SI unit and you want to get rid of the units. So you can also get rid of the units by saying target units goes to none. And then you would get a plot in seconds and in the default SI unit of the Y variable. It's most we don't use it, but sometimes this comes handy. Target unit goes to none, just to be aware of. Um, uh, and then when you use target units goes to none, then the default SI units are used. Okay, and of course, if you want to know more scenarios how system model plot is used, you can read the documentation, and we have different basic use cases, um, or the different options that you can provide. For instance, you want to simulate it longer, or you want to simulate it for a smaller duration. In those cases, you can also specify the simulation time. I'm not going to cover it now, but you can also set those options. Okay, but let's move on to the next exercise. Right. Okay, so with that, now uh, as in yesterday's session, we defined a model. We saw how to get the diagram of the model in Wolfram language, and we could now plot the results of our model using system model plot, right? The
Right.
next thing that probably that you would want to do is you want to simulate your model with a different parameter value, right? So for instance, if I open my model here, if I click on ambient, I see that I have the ambient temperature as a parameter, and I have a temperature defined here, right? And what I want to do is I want in my Wolfram language simulation, I want to uh, change that value. And how can I do that? So to do that, we use the function called SystemModelSimulate, uh, and then we call the model name. So we define which model we want to simulate, and then we can provide the parameter values option inside this association here, right? And then we can pass the parameter name and the value,
So
right?
what you are saying is, Ankit, that so we can change the parameters without using system modeler on the Mathematica notebook.
Yes, yes. So if you're working with the Mathematica notebook, you don't want to go back to your model in System Modeler and change the parameter value there, right? You should be able to
Right.
change the parameter directly in the Wolfram language. And to change the parameter directly, we use the system model simulate function with a model name, and the parameters that we want to define, we specify under the parameter values thing here. And here I have specified my unit in Kelvin. So here in this case, I have used the SI unit, 283 Kelvin. But uh, if you're not comfortable with SI unit, you can also use quantity. Uh, so let's say you are familiar with, for me, let's
Fahrenheit.
say I'm familiar with centigrade, and uh, I would like to give the value in centigrade
Kelvin.
rather than
Right.
in Kelvin. So what I do is I use quantity and comma. I define the magnitude of my quantity, and then I specify the unit. In this case, degrees Celsius, right? And then I simulate my model. Yeah. I'm getting this error when I use quantities, but you can ignore it for now. Uh, and then if I also, Vedat, if I this looks very
Right.
um, very
Intimidating.
intimidating. So one way is to evaluate this expression at place. So what I do is I select my quantity, and to represent it in a more digestible form, I do Control Shift Enter. So now you see the value, the quantity is in a more understandable or easy looking uh,
Right. Calmer.
uh, figure. But I had an issue with quantity. Like when I use quantity, you saw I had some errors. I don't know in version 14 I'm getting those errors. But uh, and if you're used to Fahrenheit, of course, when you define quantity, you can define uh, the quantity type as degree Fahrenheit, and you can specify the values like that, right? Okay. Uh, Vedat, you might observe that when we do system model simulate, we get a new object called system model simulation data, and you
Right.
might think what that is.
Yeah, exactly. So do we need to? Okay, we had plot function, right? System
Mhm,
model plot. We are looking at the bottom, and we
mhm,
could use directly the model to get whatever plot we are looking.
mhm,
So what was the need for system model simulate function?
hmm. Um,
In which scenarios we need to use it?
right, right. Uh, okay. So the thing is, when you used system model plot, you got the output as a plot, right? But imagine uh, you want a more richer output. Like you just don't need want a plot. You need a storage which has the results of all the different variables present inside the model, right? So when you do use system
Right,
model simulate, you get this system model simulate data object that contains the result of all the variables in the model. So it's not just one plot, but it lists all of them. And then if I use this data object directly with system model plot, it shows me the default plot, of course. But let me try to use this variable here that I used here. I will copy it and then I will pass it on, and then I will do it again. So here you see, I didn't have to simulate again. I passed on my system model simulation data and I passed on the variable that I want to plot, and I got the new plot, right? So when I use system model plot with a different variable, I have to simulate again, and then I was shown the new plot. But now, if by using system model simulate, I simulated once, got the entire data in a object, and then I can now call for specific variables that I want to plot and so on.
Mm.
Right? It saves a lot of my time.
Mhm. I see. Yeah, can we, Ankit, can we also get different initial values or different parameters if we use system model plot? We need to run this system model simulate for that, right?
No. Actually, you could change the parameter values and initial values using system model plot as well.
Okay.
You can
Okay.
do that as well. So for instance, let's say you want to plot something with a different parameter value. If you think that you don't need system model simulate and you just interested in the plot, you can use a similar structure, like you can define an association like this, and then you can pass it on to system model plot as well. So that option is also there, so you don't need to use system model simulate. I just showed system
Okay.
model simulate because it's much richer and it has much more information, right? Similarly, I will not do this now. Okay. So I just forgot that people have to do it as well. So let's take a 1 minute break and let people digest what we have shown so far, and then maybe I will just remove this one with the quantity so people can actually see what I have done, uh, and then I would do degree Celsius, right? So this is in the full form of what I did, and people can try to replicate this. In the meanwhile, we will call our expert Sergio and ask him to fill in if if I misspoke, or if there is something that he feels that we should add.
No, that's all good. I guess you can also maybe we can indicate also that you can indicate how many which variables do you want to store in the results, because maybe the model is really big and the simulation data can get huge if you are trying to simulate something of a considerable size. So maybe you want to store only a few variables, and that's also possible for system model simulate.
So
Um,
is it like this, Sergio? Should I put it as a property at the end of system model simulate?
no, it's right after the model name.
Okay. So you mean that I have a very big simulation
Hmm.
and I don't want all the simulation results to be included. I just am interested in one or two different variables, right?
Uh-huh. Right.
And then, for instance, this variable that I have here.
Exactly.
So you mean that I can just pass it on like this,
Hmm.
and then if I use system model simulate, then I'm only storing the values of this variable.
Exactly.
Right. So this might be very helpful if I am dealing with slow simulations or very big result files. Right.
Right.
Yes. Okay. Um right. S- right. Okay. So similarly, Vedat, uh, let me get back. Uh, yes, I have it here. Okay. Uh, there's one more thing, Vedat. Now that I showed you how we can change the parameter values, of course, for certain variables, you would want to change the initial values, right?
Right.
So similarly, what I explained before, you can also change the initial values using the same structure, but now with using the initial values this rule instead, right? So I just call initial values and provide which variable I want to change with the new initial variable. And if I simulate this everything is fine. If I plot this, I have 353 translates to around 80 centigrade.
Right.
So I have a system model plot that starts with 80 centigrade, right?
Yeah.
But there is
Seems
a catch with that.
correct.
What would happen, like if I open my model in system modeler, like if I do system modeler and then I pass, let's say, my model name, and then I call modeling. So if I change the initial values here, I plot my thing, and if I open my model, will the values change in my model?
Okay, I wouldn't expect it to be, but if it happens, it is really cool.
No, it does not change, right?
Yeah,
So yeah,
because we haven't said anything, right?
yes.
But
One of the initial confusion that happens is when you call system model simulate, you sometimes you tend to expect that if you are setting the initial values here, the values in your model would also change, right? uh, and sometimes you want that, but you sometimes as a beginner you would expect that that would change, but that doesn't happen, because what happens is when you do system model simulate of a model name, it creates a new experiment, right? It creates a new model in the background, and then it simulates it, so it doesn't do any modifications to your original model, right?
right,
but but there are cases where you would want to modify your original model from the Wolfram language. For instance, you realize that your initial temperature was not right and you want to modify the model directly. Then how can you modify that? To do that, we have a function called set system model, and similar to other functions, you give it the model name, and then uh, use define the association like this, and then I would write the parameter values option, parameter values, and then I would just like pass on the property. Rather than typing, I would just copy it here,
Right.
and I
There is a
it was
small
initial.
misspell in the parameter values.
oh, okay, sorry about that. Yeah,
Right. Mhm.
okay. And when you do this and I do set system model, right, I think it's done. And now if I open my model again with the system modeler uh, option, you could see that, uh, of course, I should have been more exact and mentioned 353.15 rather than 353, uh, uh,
Right.
because yeah, I was I was not uh, I didn't use the right conversions. But if you do that, and then if you open the model again, then you will have 80 centigrade, as you can see here, right? So in some cases where you don't want to open up your model and you want to modify it directly, then you can use the set system model option, right? Okay, fine. So, and yes, okay. uh, and also once you have,
So, Ankit, what you are saying is that now whatever analysis we do over here and we like the results, maybe we calibrate our model and then we are happy with the parameters, and
Mhm.
we can just update that thing using just Mathematica
Yes,
and get our model created in System Modeler.
yes, you're right. So let's say you did some of your parametric sweeps, which we will show
Mm.
uh, in the
Okay.
upcoming
Oh,
slides, and then you find that okay, there is one value that is suitable for your model. So once you get that value, you can use set system model directly from the Wolfram language and modify it from the Wolfram language itself. You don't need to open up system modeler, right?
right.
Also, Vedat, one more thing that one typically does when they do analysis is, let's say we use the system model simulate and we got the system model simulation data. The next thing you would want is, rather than a plot, you want the interpolation function from it. So to get those the output of your results as interpolation function, you can just use the the data object which I've stored using the sim variable name, and you can pass on the parameter for which you need the data, right? For instance, the Q flow. And then if I evaluate this, you see that I can get the results for a particular variable as an interpolating function. And then if I want to check how this function works, I can then pass it on with the other Mathematica functions. Like here, I have passed the data and I gave it a variable that I want to vary with time. And then I varied the variable t from 0 to 1800. And you can see that once I extracted the variable from my uh, simulation result, I can then pass it on to other Wolfram language functions, right?
Right. It is really cool. We can manipulate the data as we like.
Yes. Also, in some cases, you are interested in getting the time series data, right? You want to get the data as a time and value pairs rather than an interpolating function. So you can just uh, use the raw data property from the simulation data object, and then pass on the variable for which you need the time variable data. And then when you evaluate it, you see that you get a list, right? With at starting point 0, we had a different value, and as time progresses, the time changes. So in some cases, you would want the raw data because getting the raw data is very fast. So in case of I think slow simulations, you can just use raw data, so there is no complex interpolating function under the hood. Okay, and then once you have the data, for instance, and you can use, as I said, a lot of other Wolfram language functions. For instance, if I have the power data, that the power I'm losing to the environment, I want to integrate it and I want to understand how much energy I have lost, right? So I can use the
Oh, okay.
nintegrate function, and then uh, it gives me the integrated value of my result uh, as in joules.
Okay, now we are looking at how much energy the coffee
Yes,
mug
has lost
lost. Yeah.
joule. Um, right, right. So I think we'll give a minute or two for people to just digest it, and they have the notebooks. I think I didn't cover the set system model in the notebook, so they can give it a try and try to execute some of these functions. Right. Okay. Yes.
Right. We
Uh,
have a question
mhm.
from Glenn Halley. He states that make changes to them and store permanently back to the model. That is what we do with using a set system model, right?
Yes. Yes. So yes.
Yes, Stefan is asking whether we can scroll up a bit. He might be interested in something. Right, Stefan, you need to say something otherwise. Okay, is it possible to query? Yeah,
Yes. You can. So you can query.
is
Right.
it possible to query a model for its plots as variables? Uh,
Yes. I think you can use. Sergio, correct me if I'm wrong. You can use system model, right? You can use system model, uh,
Right.
pass it the model name, and
Mhm.
then you just go for plots
Plots.
or plot names or something like
Plots.
that.
Plots.
Okay,
If you really want all the variables and all the data in the plots,
right.
then yes.
Uh, yeah. So yeah, one of the plot is the coffee temperature, and then it has all the other settings to it. What happens if I do plot names? I'm just curious. Yeah. So here in our example, we had only the coffee temperature plot. In some cases, you have 4 or 5 different model plots. So querying for plot names will give you the list of 4 or 5 plots, and then you can copy this name and pass it on to system model plot. as an option, and then you can plot that. So yes, you can query all those all the plot names. Okay. Do you have to save the model after set system model? Yes. Once you do set system model, it changes the value in the model, but does not save it. So you have to save the model manually. Yes. Okay. Okay, Vedat, let's carry on. Yes. Okay. Uh, okay. So we all saw we saw how we created an explore panel uh, in simulation center, right? And sometimes it is useful to create such interactive panels in the Wolfram language. So once you have a model, you can directly create a dashboard in the Wolfram language itself. And we have a resource function called SystemModelManipulate, which helps you to do that. So let me evaluate it to see the result. Right. So what this function does is it takes a model name, it uses the control panel that you have created for your model, uh, and of course I get this unit errors. Yeah. And here you like the model that you created, um, the panel that you created in Simulation Center, you can have it in the Wolfram language itself. And then here you can change the different values. Like if I want to change it to 273, and then I would click some outside, and then you can see that the plot has changed, right? Right. Yes. So yeah. So if you have a control panel and you would want to create a corresponding manipulate of it in the Wolfram language, then you can use the system model manipulate function. And also you can use this function. Let me do Alt 7. And you can also use the system model manipulate function to create a specific, like for instance, you're not interested in the variable that is that you have in the control panel, and you want to customize the manipulate based on the things that you want to vary. Like for instance, you have a specific variable that you want to vary. So if I open my model for the coffee mug, I have different parameters, right? And let's say I'm interested in the material of the mug parameter, and I want to create a control, a manipulate in the Wolfram language where I just vary this particular parameter, right? I want to create a new panel. How can I do that? So to do that, I will just copy the system model manipulate function, and then I can pass in the 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 parameter that I want to change. For instance, here I have the coffee mug dot material of mug, and then I can pass on the range that I want to vary. Let's say I want to vary it between 1 to 12, and then okay.
In a list. So just another
Oh,
another list in the.
right.
The interval will be in a list. The range,
Is it not the right thing?
yes, the range will be in a list.
Oh, sorry.
No,
I think
I guess what the message is saying is that this is not a modifiable parameter. So this is probably being set by other.
No. I think I can modify it. Yes.
Okay.
So if I change it now, you could see that the rate of change of the cooling rate is changing, right? No, I'm getting this weird unit errors for some reason. I think I triggered something. I don't know what. But yeah. Okay, let's say if you want to just analyze one particular parameter and you want to have a manipulate like interface in the Wolfram language, then you can use the system model manipulate function, pass in the model name, the parameter that you want to vary, along with the range. So I want to vary it between 1 to 12, and then you get this nice interface where you can where you can play with your model, right? Okay, Vedat, is there any question up to this point?
Not really, actually. Maybe one question. I guess you try to explain that. Maybe some audio might miss that. Why we have that in between, like coffee mug, dots, and a material of mug.
Oh
So
yeah, okay, yeah, you're right. Uh, the thing is, when we have a model, we have three different components, right? And each component can have their own parameters. So for instance, ambient can have ambient temperature, coffee mug has its own parameters. And there are cases where two different components might have the same parameter name, right? So in order to remove this ambiguity, if we want to refer to a parameter of a specific component, we can select, we have to write the component name first and then the parameter name that we are trying to refer. Maybe in one of the future sessions, we can also lift this parameter to the top level, so we don't need to use the dot. And the most important parameters, we can increase their priority and make it to the top level. But for now, we will not see that. But that's also possible.
right. So that is the reason why we write the model name as well using dots, right?
Yes.
We just every time just open a new file, and in that folder we look for what model we are looking at, what class, and then
Yes.
want, yeah.
Yes. Okay. Yeah. Okay. But let's continue. You're already short of time. Okay. The next thing, that uh, once you have the system model simulate, here comes the power of Wolfram language, right? Now you want to do a parametric sweep. So you're not interested in a particular variable, but you're interested in a list of different variables. So for instance, let's say I want to change the ambient temperature from 273 to 303 Kelvin with a interval of 3, right? So I can use the system model simulate function, pass in the model name, and for this parameter I give it a list of values, and then I click simulate. So what it does is, you saw this was too fast for me to explain anything, but it parallelizes parallelizes the different simulations, and then once you have all the simulations run, you can then pass on the sims the result to the system model plot function, and then it stitches all the results together. And here you can see for the different ambient values how your plot curves are changing, right? And
Right.
here comes the power of the Wolfram language to do, and similarly you can expect not only one parameter value but multiple parameter values, right? And then you can
Right.
test all the different scenarios. Okay, since it's already we are already reaching the limits of our time, I will just move forward uh, so people can reproduce it later. Um, right. So once you have and I will just simulate this. Okay, so and I get this weird errors. I'll just remove it for now. Okay, so now Vedat, in the first case, we did a parametric sweep where we passed in a list of values, but there are instances,
Where we assume that we know everything.
yeah, we know everything, and then we passed in a list of values. And now let's say if you want to have a distribution, in this case, I have used an interval, so I'm assuming a uniform distribution. So each value has the equal probability of
Hmm.
getting. So here, with using system model uncertainty plot, then you can see for this uniform distribution, how would my result look like, right? So
Right.
rather than interval, one can also pass. Now I have to a normal distribution here, normal distribution, and I have to look at the options that I have to provide for it. So I have to provide a mean and a deviation. So let's say I have a mean of, this might break the model, but I will try it anyways, 273. And let's say I have a deviation of 10. This is ambient temperature, so maybe a value of 300, 310, right? And the thing is, this normal distribution I have not curtailed, right? So you know that it has a flat tail, and there are chances that we might get in some values which are at the extremes.
Right.
And when we use normal distribution, we actually use a truncated distributions around it. So if you're trying to use normal distribution, try to use a truncated distribution and limit the range based on the possible practical values. But
Right.
just for the sake of demonstration, I'm using a normal distribution for my ambient temperature. And what it does is system model creates 200 different simulations using the random variate function. So it picks different values uh, following this distribution, and then it tells like what is the most probable uh, answer, what is the most probable expected value, and how is the spread. So once you
Mhm.
pass in the distribution, you can get the results that follows that distribution. Perhaps Sergio might have something to add here.
Yeah, we can change the number of 200, right? We are not limited to 200. It is
Yes,
just the default value, right,
Mhm.
Sergio?
Yes, exactly. You can change that as well. You can change the kind of distribution that you want to use. We have a lot of possibilities to explore in uncertainty plots. So you can also find them in the
documentation.
documentation. Yeah.
Yes, let's move forward. We are already
Right, we are running late.
uh, anyways. Okay, I think, yeah, okay, I will be quick. Okay, so sorry, people, I might be too fast for people to try out things live, but I just wanted to show it so people can take that time later on and they can try it out. But the next important thing I wanted to show, and perhaps a list line plot shows this better. So let's say you have a experimental data. So you took a thermometer on your on your coffee, hot coffee, and you measured at different time instances, right? And now the next thing that you would want to do is you want to calibrate your model with the measured data. And
Right.
because
What can we model in such model, Ankit? What
uh,
can we calibrate?
okay, so the thing that can be calibrated are the parameter values, right? In the model,
Okay.
I showed the different parameter values that you can tune. So let's say if you have to match your model with experimental data, you have to create a control panel with all the parameters and manually tune each of them, right? Or you have to manually find the right value. But instead of doing all those things manually, you can use the system model calibrate function, which takes in. Uh, so here we have defined the data. Now for this function, we pass like which is the model variable for which we are passing the data, right? So we are defining how this experimental data should be matched with which variable data in the model. So with this step,
Right.
we are just mapping them together, right? And once we map them, then we define the model that it should use and also some constraints, because but I should just evaluate this so that we, it calibrates while we
Yeah.
discuss. So to this calibrate function, first you do the mapping with the experimental and the measured data. Then you pass on which model you're talking about, right? You have to define the model name. And then you can also give a constraint to it, because if you don't give a constraint, it will just it has infinite space, and then it might reach some local minima and it might be stuck somewhere, right? So it's good to define a limit in the which is more realistic, and then you can pass on the parameter that you want to calibrate. So in this case, I want to calibrate the model of the material of my mug, because either it is made of ceramic, glass, or steel. The conductivity value will differ. And now let me just stop my results at this stage, and then let me uh, here alt 7, enter, yeah.
So we don't need to wait it stops, right? If we are satisfied, we can manually stop.
Yes,
The
yes.
calibration,
So
right?
so if
Okay.
the results, yeah, right, for some reason my mathematic is stuck. Okay, if you are satisfied, because when you saw the nice display, it also tells you what is the level of error, and if you are happy with the error, then you can stop and let it return a partial result, right?
Right.
And to compare it, let's just give me let me store it in two different variables. I call this as plot1 and I store this as plot2. I will add some styling to it. So I will say plot style, so that I want to compare with my experimental data. So I'm just trying to distinguish it. And then I want to have the target units goes to none, because I have my experimental data in seconds and this is returning me in minutes. But so
Okay.
that's why I'm trying to use that. And here you can see this is my result in uh, in seconds. The time unit is in seconds, and the top, this is my experimental data, and here the time unit is in seconds, right? And now I want to compare them. I can use the show function and then pass in the plot1 and plot2, right? And you can see with this data how it was able to
Yeah. Match.
calibrate, right? And then we have this calibrated model. You can use system modeler and then the calibrated model and try to see the parameter values that was obtained. So if I do
So
system, let's say
I'm
I,
get.
yes,
Yeah. Yeah. We are getting question about a number of variables. Are we
mhm.
limited to one, or can we use more than one?
uh, we can use more than one, but Sergio will be able to answer that.
Yes, you can fit more than one variable. We just set the optimization problem to try to fit all of the variables simultaneously.
Yes, and with that, once I got my calibrated model, I use the system modeler to open my new model. And if I open it and select my coffee mug component, I can see that the material of the mug has been modified and it's around 5 that I'm getting.
So
So
this is totally a new model, right? And not the model
yes,
we
it's
set system
a
model for.
totally new model. So it uses experimental data. It takes our original model and it returns a new model from it with the new calibrated values. So
Okay.
it does not destroy your original model, because it might not be your intention, right?
Right.
To
Right.
calibrate the parameter there itself. Right. Okay. I will take 5 more minutes. uh, so, and here I made a mistake. I will just change it to 2023. If you try to do this with 2024, you might not get the right answer because Wolfram language does not have the data for April. Okay. So far, okay, I'm just trying to cover so much. So sorry about that. So far, Vedat, we saw how we can analyze our model, how we can use the system model plot and system model simulate function. We saw how we can do parametric sweep, create a dashboard, and we also quickly just went through uh, how we can use system model uncertainty and system model calibrate functions, right? So the
Right.
analysis part is done, but quite often when you are using the power of Wolfram language is also being able to create models from the Wolfram language. And in the remaining time, I will just cover three different common use cases, right? The first use case is, let's say you can use the wind speed data and uh, uh, get a time series data from Wolfram language, and then you want to pass on the time series data so that you can plug it to your models. For instance, let's say you have a wind turbine model, you want to pass it a wind speed, and then you would want a data of the wind, right? And that data you can get it using the wind speed data model, get a time series, and then use a function called create data system model. And you, so people who might be confused with this time series shift that I did here. So what I'm trying to do here is when I got this data, I have my times in dates, right? Because this wind speed data gives me a date list plot. But in my model, I have my simulation starting at time 0 onwards.
Okay, it is
So
in
that's why I
seconds
try
as
to,
well.
I'm using this time series shift so that my wind speed data starts from the 0 value. And once I have this create data system model, I can plug it in to my other models. I will not show it today. I wanted to show it, but I don't have time. And then I'm just plotting. Okay, maybe I need to assign the data here. So I've used data model. So I'm creating a new model from the data, storing it in a variable, and then using system model plot to just plot the output from this new block that was created. And yeah, let's see. Yeah, so you can see this is the output of the model. Y1 is the name of the output variable. Y is an array, and we are accessing the first element of the array. That's why I've used Y1 as a plot variable. But you can see you can get the similar response.
So the time also changed automatically. It
Yes, the
was in
time.
days and then
Yes, it was in days, but then when I did time series shift, it changed, and now I have it in seconds.
so it changed according to experiment simulation setup, right?
Yes,
I mean,
yes.
if we have in simulations while setting the simulation system modeler, so it will come out as seconds. If it was like in days, we will see here as well as days, right?
Um, I think so. Yeah, but yeah, yeah. You can change the
Hmm.
time unit if you want. That's fine. Okay, but the next. Okay, so perhaps in the later sessions we will explore more into this. But for now, I just wanted to say that if you have a time series data, you can create a model from your time series data, and then you can plug that time series data with your other models. Perhaps in the later session or in the upcoming session, we will see an example where we use this kind of things. The other thing is, uh, let's say you have experimental data and you have relation between two different variables, y versus x, right? And then you have a no, so you have a nonlinear fit. And what you want to do is you want to create a block in system modeler where you pass in x value and you get a y value out of it, because a lot of times so all your models might depend on empirical relations like derived from experiments, and in those cases you rely on model fitting rather than equations. And in those cases, once you have a fitted model using Wolfram language, you can pass it on to create system model function, and it will create a block for you. So you can pass in the x value, and then you would get back the y value from it. And this also comes in very handy when doing real world systems where you can combine your physics model with a fitted or experimental model. So this comes in handy. And to quickly check this, if I open it in System Modeler, yeah, you can see this block that was created for me. And if I include step one, uh, right, I didn't save it, but yeah, and you can see under the hood, it created all the equation for me, and then I can just pass in the y value and u value, and I will get back the y value. But yeah, yeah, okay. Finally, I just want to quickly cover that apart from the time series data and the fitted data, as we saw, you can also create models from equations. In this case, we are modeling the bouncing ball problem. And here we are defining how the velocity is changing with height and how the change in velocity is related to acceleration. And then we have events. So, so like when the height reaches 0, something happens in the system, right? Some equations are changed. So you can pass on those kind of equations as well. And you might notice that these equations are not simple continuous systems. There are events inside it. So it's a combination of discrete events and continuous events. So those kind of equations can also be passed on to create system model function. It creates a model from it. And then if I simulate and plot my model, you would see how the model responds. This was too fast, I understand, but I just wanted to let people know that this kind of analysis is possible, and there are numerous different ways of creating models. You can create models from CAD objects with the mechanical properties as well, and you can create you can connect models together using the Wolfram language. So you don't need to use a drag and drop environment. If you know the model name, you can use a new function called connect system model controller or connect system model components function, and then connect them using code, right? So you can automate the entire drag and drop process, which I have not covered today, but that is also possible. Right. And if you want to know more, you can visit the system model overview page where all the different functions that we covered today are listed. And if you go into any of this function, just like any other Wolfram language functions, you will have the basic uses, options, and different ways of doing things. And you have any questions, please feel free to post it in the community and we will be happy to answer.
Right.
In the remaining 1 or 2 minutes, I will just ask Sergio, who is the main guy behind this integration, uh, to correct me if I said something wrong or if I should have mentioned something.
No, I believe this is everything was good. and I guess the most important thing is, as Yankit mentioned, that we are very friendly. You can reach out to us, and we'll help you with all your needs.
Right. Right. And I have a question that how can one import data to use with System Modeler? So we use the create data system model, right? So once you import a model which changes with time, you can pass it on to create data system model, and you can use it. And if you have a relation between y and x, like as you saw in this non-linear model fit, those kind of data also you can pass it to create system model, and it will create a block that you can use it, right? uh, okay then, sorry, we had an extended session today. We had quite a lot to cover, but please feel free to try out the different functions that I showed today. Of course, you might notice that there were some modifications that I did in today's notebook, which is not the same as the notebook that is shared in the shared folder. I will try to update it for tomorrow, right? So you will have access to the new notebook with the updated functions so that you can refer to it later on. Yeah. Okay. Okay then. So that's all from us for today. And please post your questions on the community if you have any. Thank you.
Thanks for your attention, guys.